Hello and welcome to today's Academy presentation. Today, it's Scott Bootler giving you the presentation from Langley, BC. And our topic today is, this is actually round two. We did this last week, but application and piping for condensing boilers is our topic of discussion. This is a 200 to 300 level training session. So the idea here is last week it went pretty well. It's lots of information in here, so I will kind of mention that. And we have it posted for an hour. It's going to be closer to probably 90 minutes or so of information. Lots of stuff to cover here. But the idea with this presentation today will be to kind of mingle in the 200 and 300 level series controls and how those controls will help you with your application, and then also mix in there some of the piping strategies that we deal with, because with the 200 series boilers and the 300 series boilers, there's some different looks as far as what that piping might look like when you finish your system. And the whole goal here is to kind of explain how to kind of create and maintain an efficient heating system. And at my side virtually today to help me with this presentation is Academy instructor out of Waterloo, Ontario, Mark Norris. Are you there, Mark?
I am, Scott. How are you doing today?
I'm doing quite well, thanks. Quite well. Looking forward to going. This is our last presentation. Well, my last presentation until the new year. So hopefully get off here on a good start and a good ending. But what are you up to today?
Well, I've been working on my presentation for VitaGate in the next couple of weeks, so that's been what I've been doing mostly this morning.
Excellent.
And looking at some of the new stuff we got going, and we're going to have a lot of new products in 2021, and trying to work on the development of those things. So it's some exciting stuff coming. So you guys will want to pay attention to that, because there's a lot of game changing stuff on the plan for the 2021 product.
Yeah, absolutely. So I'm looking forward to it. Pretty excited about what I've heard trickling in or whatever of some of the new stuff that is coming down the pipeline. Looks like it's going to be a really interesting stuff and a lot of fun to talk about. But we should get into this one here today, because it's there's quite a bit of information. So Mark's going to look after the Q&A for us today. So kind of our little team up here is when I do the presentations, Mark is the man on the controls, and then when he's doing the presentation, I am looking after the Q&A on that side as best I can. I'm not certainly on the tech link here. You're talking to the weak link of the pair here, but so
if
let's get going on this
today, guys. Ask them in the question and answer box. We collect data very efficiently that way, and then we can send out at the end the questions and answers as a PDF to you. If you ask them in the chat box, we don't get all of the data. It's not designed for that. So if you want to ask a question, ask it in the Q&A box. I will try to keep up with Scott in real time, and anything that we can't answer, or I can't answer, or we have to wait till the end, we'll do those verbally at the end. So back to you, Scott.
All right, so I've had my coffee. I should be ready to get going here. So we've got, as I mentioned, a little bit of kind of work to go through here. But the idea is that we're going to talk a little bit about here initially, just talking about the differences between a condensing and non-condensing boiler, just to get our heads wrapped around the differences in efficiencies and where they're going to come from. So we'll take an example here. You see in front of you two boilers, one non-condensing, the other one a condensing boiler, and based on the conditions that we're dealing with today, the supply temperature to satisfy the spacing requirements of these buildings is about 120 degrees Fahrenheit. So right off the bat, you can see the difference here is that the condensing boiler will operate at the supply temperature that is required for the building to maintain that comfort level. Or a non-condensing boiler, there are some differences there. It can't hold that temperature as far as it can only go so low on the set point. And there's a bit of a limitation there on the non-condensing side of it. As far as losses and gains, all those types of things, we got to start looking at the difference between the amount of energy that we're putting into those boilers. So as the fuel goes in and we burn that fuel, what we're trying to find out here is there anything that we can deal with as far as standby losses? So when we define standby losses, what we're looking at here would be the amount of energy we burn versus the amount of energy that actually went into heating the space that required the heat. So if we've lost some of that energy in different areas and didn't make it to the actual zone or radiator or floor that was requiring that heat, then we would call that a standby loss. And hot boiler rooms are notorious, obviously, for standby loss. We're heating a space that really doesn't require heat. Some people argue, well, that insulates some other areas that may require heat, so that you actually don't lose all of that energy, because it does help buffer different areas of the building. Uh, if you've cleaned enough boiler rooms or gone into enough boiler rooms, over time, where the temperature outside is, mid 80s, and you walk into the boiler room and you're up in the mid 90s or hundreds, you're sitting there drinking a gallon of water to clean the boiler. Those are standby losses. That's energy basically that's just dissipating into a building that we don't need to heat. System piping, so the hotter the water temperature, that supply temperature going out, of course, the more loss going through the piping as we pump that fluid up to the different areas of the building. Is it getting lost in unconditioned spaces, etc.? So those are losses. Draft in your venting. Some atmospheric boilers out there, you might have, the damper is, stuck open. It stopped working years ago, so they jam the damper open. Of course, that's just draft that we're dealing with in there. Any post purging of boilers after they fire is another, standby loss, basically, as you pull that combustion air through the boiler and it's not firing. It's going to heat that air up and it's going to dump it outside. So you're losing some energy there, efficiency. So every time your burner cycles and then it goes through a post purge, you're dropping your efficiency of that particular unit as well as a standby loss. So all those things kind of add up here. Looking at the losses from the jackets, even your condensing boilers are going to lose some energy in standby loss. The As I mentioned earlier, with non-condensing boilers, it's that maintaining that temperature threshold. So we actually don't have that boiler in basically unsafe conditions as far as the boiler goes, where it starts to hit dew point inside the boiler and we start getting actual condensate in a non-condensing boiler, which will be bad. So all those things kind of add towards that increase in standby losses from a non-condensing to a condensing boiler. So we're conservative here, about 5% on the non-condensing, about 3% on the condensing boiler with the temperatures that we're looking at in this application. So there's standby losses. That's just physical, sensible temperature loss of the cooling down of the boiler as it sits there in a standby condition. But when the burner's firing, there's losses as well. So we have a look at the combustion side of the boiler. So when we put that fuel in there, we add a spark and we fire that burner up. What amount of energy that we're utilizing that fuel is actually going up to heat that radiator in the building that we need to supply 120 degrees to. If we look at the stacks here, you can notice that right off the bat, the stack and the amount of exhaust gas coming out of the non-condensing boiler is much larger than the condensing boiler. And that's because there's a lot of energy in that vapor. So there's going to be more vapor coming out of a non-condensing boiler vent than a condensing boiler vent at the temperatures that we're looking at here. A couple of the areas where we're losing some efficiency. So as you measure the temperature in your stack, for every 50 Fahrenheit change in that stack temperature, that's about a 1% increase or decrease in your combustion efficiency. So if you put your combustion analyzer on there, and we see that the condensing boiler here is sitting at about 125 Fahrenheit, where the non-condensing boiler is sitting at about 325 Fahrenheit, you can see right there's a difference of about 4%. As far as efficiency. When we are talking about condensing boilers, when we get the unit into condensing range, that typically the temperature of the stack is going to be in that 15 to 40 degree temperature difference from the return temperature coming back to the boiler. So there's kind of a matching there. The lower the return temperature, the lower that stack temperature gets as well. And of course, that's the desire of condensing boilers, is to get that stack temperature down as low as possible, as we'll see here in a minute. Non-condensing boilers, also, you want to protect the system. And part of that system is the vent. So the venting, we want to make sure that flue gas makes it outside of that vent without hitting the dew point. And sometimes that might mean, making sure that there is a minimum temperature hitting that stack so that all that flue gas can escape without without condensate being formed in the venting, and of course that can destroy the materials of the non-condensing boiler here. So there's a few things here that are built by design to protect the non-condensing system from premature failure, and there's other areas here just by the design of the boilers themselves where we start to gain some efficiencies here based on condensing versus non-condensing. So having a look at that, so there's a sensible temperature we just looked at, but as far as the latent heat, or when we talk about condensing technology, when we boil water and we get that water going from a liquid to a gas, basically the temperature of the water is not changing. We hit that 100 degrees C or 210 Fahrenheit. And in order to get that steam formation, we have to add about another 970 BTUs for every pound of water to completely boil that water off and create steam from the liquid. Same thing happens in a condensing boiler in reverse. When we have that steam, with vapor being formed in the combustion process, and we cool that flue gas down to a point, once it converts into a liquid, as we basically get about a pound of that liquid being formed to a pound of water or condensate being formed, that's about 970 BTUs of energy we've actually brought back into the heat exchanger. So that instead of it going out as steam and going out in the environment, we actually pulled that as usable heat back into your heating system. If you equate that to about a cubic foot of gas, which is right around 1,000 BTUs per cubic foot, it's really easy to kind of make an equivalency there. For every pound of condensate you see coming out of that boiler, that's about a cubic foot of gas savings as far as the amount of energy that we're actually saving. And up to 10% of your natural gas energy is in that vapor. So there is a lot of energy that's sitting in that. If we can extract that energy and have that boiler basically start condensing, then we're going to grab that 970 BTUs per every pound of water, and that's going to be used to heat the building instead of going up and protecting the chimney or escaping out in the environment and just basically lost forever. Your analyzer is not going to be able to pick that up though. So as you look at your combustion analyzer, it doesn't add that condensate back into your efficiency equation. You have to basically, as a measuring here, if you measure the amount of condensate, this is pulled from our technical data manual based on the numbers that you see here, 120 to 100 degrees. Condensate flow out of this boiler would be about 0.8 US gallons an hour based on the information I have here as the burner's firing. So 0.8 US gallons an hour is about 6.64 US pounds or pounds of water, US pounds. 970 BTUs times 6.64, you got about 6,441 BTUs of energy. And we have to add that back into the 100,000 BTUs of input that we've actually put in here to add that back into our efficiency. So of that 10% of that vapor that has the energy in it, we've extracted about 6.5% of that full 10% in this little exercise. So there's the Viessmann Wiederden's heat exchanger. You can see the condensate being formed here as that flue gas moves through the passageways, and this is the stuff that is basically saving us the gas or the energy that we're putting back into our heating system. This is not going out the stack anymore. It's being drained out of the boiler instead of coming out as a plume of steam. So on a non-condensing boiler, we lose that 10% of latent heat right there. And of course, the temperature of the flue gas that we looked at, there's another 6.5%. So the total amount of energy that we lose out of the 100% is about 16.5% out of the stack. We lose about 6% out of the condensing boiler stack based on the temperatures that we just looked at. Now, it is possible, obviously, if we wanted to, we could get that non-condensing boiler to condense as well. And you can see the impact here of a boiler that has been condensing when it shouldn't be condensing. You can see that basically the materials aren't made for that. So there's no magic in the condensing boiler isn't in magic as far as how it utilizes or condenses. That's all by design. And as long as we are maintaining a return temperature back to the boiler that's down below the dew point of our gas, then that boiler is going to condense, whether it's a condensing boiler or a non-condensing boiler. And that goes the other way as well. We can have a condensing boiler with 95% efficiency on the side of it, but it could be operating at the mid 80s because it's in a non-condensing range. So the importance here is the fact that the boiler itself doesn't determine whether we're going to condense or not condense. It's really the system that determines whether we're going to condense or not to condense, and that could be to advantage or that could be to an extreme disadvantage based on the actual boiler that's installed on that particular site. So when we actually look at the useful heat, so out of the 100% of the energy that we're firing in a condensing boiler, about 91% of that energy is going in based on the temperatures that we saw here today in this little example. Whereas the non-condensing boiler, you're at about 78.5% of that energy actually going in. So when you look at those boilers, you see, the non-condensing boiler might have had a AFUE on it of 86.5%, the non-condensing boiler of 95%. And but sometimes you see these energy savings when you do a replacement of a condensing and pull that non-condensing boiler out and put a condensing boiler in, a 30-40% energy savings. And this is kind of where that starts to get aggregated when you start looking at the standby losses as well as the operational losses of that boiler over an annual period here, and you start to see the differences here where you start getting into it might only be a 10% AFUE difference in the boilers, but as far as operation, you can get 30, 40, 50% difference in energy differences between the two of them. And that kind of gets us into the high efficiency heating system. So as far as a condensing boiler, it's part of that whole strategy of getting into high efficiency. So basically mitigating the amount of losses we have and increasing the amount of useful energy that that boiler is delivering into our system. So the goal here is to maintain that, that building envelope here, the occupants inside at a comfortable temperature, whatever that might be, with whatever type of functions going on inside the building. The other goal here is to utilize as much of that energy we just looked at, to make sure that it's all usable energy, as much of that as possible when we burn that gas, that we actually deliver that energy into the building as useful heat, and to make sure that we safely operate and protect the system from damage. So, to ensure that all the components here are in a good operating condition and they maintain that good operating condition throughout the lifespan of that boiler. And that will just go towards a much longer strategy. The more problems you have, the more costly that system is going to be. So the C here is important as B is as important as A here as far as the goals that we're talking about. The challenges we have with this type of efficient heating system is we have constant changing goalposts. So basically the exterior and exterior conditions are always changing. The temperature outside is dropping, it's increasing. You might have, bedrooms, you've got, you might have exercise rooms in a building, all different areas where people are doing different types of functions. You got to keep all those people comfortable. So lots of challenges in there. And then as far as modern heating systems, these efficient heating systems, you might be controlling multiple temperatures in those buildings now, multiple loads, different types of, loads, snow melts and pool heating and different, domestic hot water loads. Zoning is a very important part. Mark just did a presentation a couple weeks ago on, zoning systems and multiple temperature systems, which if you haven't caught, you might want to go back to our archives and have a look at that. Really interesting information on that. In regards to what I'm talking about here today as well. Priorities in your system, so domestic hot water priority might be part of that system. Essentially control complexity, and hopefully some of the information I give you today on our controls will basically kind of pull the shroud back a little bit as to how our Viessmann controls can help kind of make that side of it a lot easier and a lot, because our controls basically integrate the burner, the boiler, and the actual system as well. So everything kind of works together for efficiency, and that's kind of helps towards that whole goal. So what do we know about, heating a building? So essentially heat losses, what we understand is, as far as an indoor temperature, it's fairly consistent. As a matter of fact, we start looking at heating curves. When you actually do a heat loss calculation on a building, you're going to actually select a temperature that you want to maintain the indoor environment in as part of that whole process. So we're gonna grab a temperature for the indoors. We do a heat loss calculation. So that typically is a fairly consistent temperature that we're dealing with. The changes are on the outside air. So as we go from spring into summer, into fall, into winter, of course those temperatures are changing vastly, and that has a direct impact on that particular indoor environment. So of course the warmer the temperature, the less heat we're losing to the outside. So as that temperature outside difference in temperature changes, that's going to vary the indoor environment. So as the temperature outside gets much colder, then of course we're going to accelerate the loss of the energy from the building to the outdoors, depending on what we have as far as a building itself, how well it's been insulated, et cetera. But it will still have a change. So as that, even a well-built or well-insulated building, the colder it is outside, the more heat it loses, and compared to how when it's a little bit warmer outside. So there's some challenges there that we're going to deal with. But now that we understand, the heat loss of the building is basically we set a temperature inside, and then what we're trying to do is maintain that temperature as everything outside is changing. That's our challenge, to keep that system in operation. So in order to kind of have a look at just what we're talking about, let's have a look at my little neck of the woods here up in Vancouver, British Columbia, just outside of Vancouver, in a little town called Langley, BC. And you can see our operating hours here in Vancouver for the heating season. So what we're saying here is 20 degree C or 68 degree Fahrenheit. We don't need to heat anymore. So that's our indoor temperature we're looking at, about 68 degree Fahrenheit indoors. When the temperature outside is below 68, we need to heat the building, because it's going to start to transfer energy from the inside to the outside. And you can see that in Vancouver here, we spend about 1,168 hours between 20 and 12 degrees C, or 68 to 54 degree Fahrenheit. Another 50% between 12 and 5, between 5 and -2, about 1,858 hours, 198 hours between about -1 and our design temperature. So this is historically based on weather data that's been calculated, or basically gathered for a number of years. About -9C, if I would take a set of plans to a heat loss designer in Vancouver, this would be the number they would use to say, based on the area that this home is being built, I have to make sure that we can maintain the indoor environment when it's as cold as -9 degrees C outside. So the difference between what we're looking at as far as comfort, 68 degree Fahrenheit indoors, and a -16 degree Fahrenheit outdoor temperature, this system basically has to deal with about a 52 degree Fahrenheit delta T between the indoor and outdoor as the coldest time of the year. So totally what we're looking at here, as far as total heating hours, that we are down below 68 Fahrenheit in Vancouver, is about 6,536 hours. But what you'll notice is a very small amount of that, 198 hours, is actually spent at those very cold design temperatures. So of course the temperature here is changing, and of course our building heat loss is going to change along with that. So you see the outdoor temperature here in the horizontal. I haven't quite caught on to this area here yet. We'll talk about this here in a minute, but you notice these temperatures on the vertical axis here. And what determines the supply temperature here going out based on how cold it is outside, we're going to have a look at here in a couple of minutes. But just kind of be aware of the outdoor temperature down here on the horizontal, and the required supply temperature here is going to be on the vertical. So having the same look at a different city here. So in Winnipeg, Manitoba, I picked this one just because it's got such a variance as far as temperature. So instead of -9, we're all the ways to about -34C, about -29 Fahrenheit as the design temperature in Winnipeg. So if I'm building a house in Vancouver, I'm designing for -9. In Winnipeg, I'm going to design for -34. So of course, the heat loss is going to be much higher in a building built in Winnipeg, Manitoba versus Vancouver. But as far as the total hours, they actually spend about 100 hours less heating season below 68 Fahrenheit than we do here on the coast in Vancouver. So they have a little bit more time spent above 20 degrees C in a year than we do here in Vancouver, even though they have a much bigger spread as far as the temperature here. So same idea. Where does this temperature here come from on the vertical? We're going to have a look at that here in a minute. I'll introduce another line here, and we talked about this when we talked about the examples of condensing versus non-condensing, that dew point temperature. And based on some other variables that we don't have enough time to talk about here, but basically how well your burner is actually utilizing the fuel. So that's how well your combustion is. Typical dew points for natural gas would be somewhere around 130 Fahrenheit. So that means once the flue gas gets down below this temperature, it's going to start to create condensate. If it stays above that temperature, then we're going to have flue gas or vapor moving out of the boiler and into our stack. Now, you might have that gas convert into liquid in the stack in a condensing boiler. That's possible. But that is not really going to add the efficiency back into your heating system, because that's going to maybe drain out of a drain tee in some applications. With the Viessmann 200 boilers, and the 100s, it actually, that condensate, if it develops in the venting system, actually drains back into the boiler heat exchanger, and you'll get actually some extra sensible heat out of it as it drains out through your drain pipes. You actually do get a little bit of that sensible heat back into the boiler, even though you had some condensing in the vent versus in the heat exchanger itself. But the goal here is to have that flue gas hit that dew point temperature in the heat exchanger to grab that energy. And of course, you can see these temperatures up here are above that yellow line. So that might cause some challenges to get those boilers to condense. But anything down below this line, as far as operation, you're already in condensing. So it's pretty easy for the boiler to condense at those low temperatures. Let's have a look at our boiler. So we see the temperature, regardless of where we are. You know, it could be in Vancouver, Winnipeg. You could be sitting, somewhere on the East Coast, central the U.S. or central Canada. But those temperatures outside, as we know, change from summer to winter to fall, the areas that we need to heat buildings at least. But because it's varying, our condensing boilers also vary. So you can see, here's 5 boilers that we have available. In the Viessmann 200 series of boiler, it looks like this in the heat exchanger. And they have a rating of 12,000 BTUs up to 6,800,000 BTUs. So they got this basically this change or modulating BTU input. Have a look at the sensor number 3. We'll kind of remember this. Our CU3A, or Vito Crossel 300 boiler. So the 300 level boiler here, same thing. It's got some modulating capabilities. So it has a high fire and a low fire. So typically a 5-to-1 ratio on the CU3A boilers, as far as going from low to high and what we can get out of it. It also has a number 3 sensor here, and the importance basically of what your boiler can do here. And this is not even with any outdoor reset, just essentially having a changing temperature outside, and of course the loads of your buildings changing along with that temperature, increasing and decreasing with the change and fluctuation of the air temperature. It's important that your boiler will be able to react and pick up that load as well. And without an outdoor sensor, how does the boiler do that? With our units, what a burner is going to do is anytime you fire that burner, it's going to have a set point already adjusted. So it's going to have a goal in mind. So anytime a burner fires, it's just not random with an input sensor like we have in these Viessmann and Vito Crossel boilers, number 3 sensors. So when the burner fires, it's going to basically start monitoring this number 3 sensor. And if in low fire, so the burner fires off, it drops down to low fire, and it sits there and monitors that number 3 sensor. And if the set point is actually increasing, so if the temperature here is actually increasing, the sensor's picking up that we're actually increasing supply temperature on low fire, then that burner is going to stay in a low fire position because it has an anti-cycle logic to it, which means that it doesn't want to ramp up if it knows it can meet that set point at the lowest firing rate. So of course, the whole idea is that once that burner fires, we want to keep it running as long as possible, but at lowest firing rate as possible as well is the goal here. Versus if we had a lot of load, so more zone valves open here now, and of course the temperature here is dropping off instead of picking up, then that burner logic is going to basically say we've got a larger load, and the burner is going to start to ramp up so that we can satisfy that building load at that particular point. So it's pretty important that the boiler control logic includes some method of having a sensor feeding back to the boiler control saying, we're good. We don't have to ramp up any higher than this because we're keeping up with the system. Actually, we're catching up to the system as far as operation, or we got to modulate up because we got a larger load. The temperature is dropping off on low fire. We got to start ramping that percentage up to satisfy the load. And the desire here is twofold. Obviously, keep the burner running as long as possible with that whole anti-cycle feature, but also if your burner is operating a low fire, it is your heat exchanger is well oversized. So if we looked at this Vito Crossel 300 with a 5-to-1 turn down, which means that the burner can drop down as low as 20% of its maximum input, that would tell you with this boiler on low fire, it's about, the heat exchanger is about 5 times bigger than what it needs to be for that firing rate. So that heat exchanger is going to be able to basically suck the energy right out of that flue gas or combustion that's being created, and it's going to pull that stack temperature down. So that's where the energy basically is moving out, sensible energy, and potentially you can actually drop it down low enough where we actually extract enough energy out to get that boiler to start to condense in that low fire position. So the advantage here is that lower firing with condensing boilers, you get actually more efficiency out of that unit because that heat exchanger is well oversized for the amount of BTUs we're throwing into it, and we can extract that out very easily. So you get two benefits there with this anti-cycle logic. You get the burner staying in low fire, extending the run times of the boiler, and you get the ability of a higher efficiency of the boiler as well in that low fire position. So as we fire these units, so that's even without the outdoor reset. So now let's have a look at as we start adding this to the boiler. So what if the unit now, your boiler sitting in your boiler room, we threw a sensor on a wall outside, preferably the north wall where we get basically the coldest area of our building is going to be the north side. And we wire that back to the boiler, and we tell the unit, you're going to fire, but just so you know, the temperature outside is this today. And as we do that, now your boiler can be controlled based on how that temperature outside is looking. So the colder it is outside, you're going to be losing more heat, as we know. The boiler is going to fire to a higher firing rate. If it's a little bit warmer outside, then it'll be firing at a lower firing rate, essentially to maintain a comfort level in the building without hitting that temperature too quickly. And of course, this will help us. The outdoor reset side of it's going to help us with that, achieving that, the goals of the efficient heating system. You see the goals here, obviously that comfort we talked about. And then of course the energy savings is the other side of it. So you see this family sitting here, they just paid their fuel bill and now they're all sitting there talking about where they're going to go on their next vacation, right? So they're taking they're sitting there in their comfort and they're talking about what are we going to do with all this money that we saved, putting this new heating system in. I'm thinking that the young fella here probably said he wanted to go to Vegas to play some blackjack. Maybe that's what it was, maybe what's going on there. So as we add outdoor reset to our heating system, so we're back to our graph here showing the heating season or the hours of heating time in Vancouver, British Columbia. I've thrown the heating curves in the background there so you can have a look at that now. And how we set this basically is we have to know what temperature we're going to need here on the axis based on, and then we can select our heating curve. So it's all about, we have a heat loss that we're going to calculate based on our outdoor air temperature, indoor air temperature we're trying to maintain. We have a supply temperature here that we're going to pick, and that's going to be based on the type of heat emitter that we're going to include or basically install in the buildings, whether it's existing or it's a new home construction. The type of heating system is going to directly relate to what we're going to select here as far as a heating curve. Some of our information in our manuals will kind of depict different areas, give you some recommendations on what heating curves to select here. But the whole idea here effectively is that regardless of the type of heating system that we are going to install, it is possible to get these boilers to condense. And sometimes it depends on how quickly we want the boiler, or can we get the boiler to condense. So in a new home construction with a copper fin baseboard system here, we've grabbed the engineering data of a piece of baseboard we've thrown here on the bottom. And of course, as a designer, what you're going to do here is if we effectively picked a building here with 50,000 BTUs of heat loss at our temperature outside, maintaining our room temperature inside here. We've put in, we've taken that 50,000 BTUs, we split up into 4 zones. So each zone we've designed basically for about 12,500 BTUs of heat loss per zone. We put 25 feet of baseboard per zone in here, and based on our information that we have at 12,500 BTUs of heat loss at 25 feet of baseboard, we could calculate what that supply temperature needs to be. So when we have a design temperature here of 180 degrees, returning back to the boiler at 160 degrees, so there's our delta T. 180 minus 160 is a 20-degree delta T that we're working with here. When we do this, basically our average temperature is going to be about 170 degrees. So we take 180 plus 160 divided by 2. We see that the average temperature going through the baseboard at these design temperatures is about 170. We multiply that 510, which is what we get per linear foot of baseboard at 170, multiplied by the 25, and you'll get about 12,500 BTUs. So how we select the heating curve here is we know we need 180 to maintain the heat loss at our design. And this is what we would select, a 1.80 heating curve to make sure that we achieve that particular temperature. So that means that as far as our condensing application, this 1.8 heating curve is going to basically stay above the dew point temperature until this return temperature drops down below the dew point of our flue gas. So somewhere around that +3 outside temperature, we're going to start to get some condensing going on in the boiler. And as it gets warmer outside, of course, as we start dropping lower and lower, we start getting more and more condensing going on inside the boiler, more and more efficient operation. But instead of designing for, instead of 25 feet of baseboard, if we added another basically 30% more baseboard into that system, so another 8 feet of baseboard per zone, what that would do is we can now drop our supply temperature down to get the same amount of BTUs because we have more linear feet of baseboard to work with. Now the average temperature is 380 degrees, so 160 to 140, still a 20-degree delta T that we're dealing with here. But if we multiply 33 by the average temperature of 380 degrees of BTUs per linear foot of baseboard, we would get that 12,500 BTUs basically per zone that we're looking for. Now we see that that temperature can be achieved at our design outdoor temperature at a much lower supply temperature here now. So basically the heating curve now is going to be about 1.5. And the difference here is now instead of a hitting dew point at about +3 outside, we're down to about -2 outside here now. So about 15% more of our heating season, we are actually going to be condensing with another 30% baseboard. So you do the math on that. Is there a return on investment there by adding more baseboard to get this boiler to condense earlier? If you start thinking about year over year, absolutely, that commodity is going to pay for itself in a fairly short order, the quicker we get this system to start to condense here. But there's some other things we're going to look at here as well, as far as that, even that reduction in that supply temperature, that is going to save us some money as well. The same thing here if we look at a fan coil. So another high temperature application, low mass fan coils. Viessmann makes a couple of fan coils, if you're not aware of. We have these, we call them Airflow Plus. Model numbers are AH2A, 213 up to 385. So a building here, 70,000 BTUs of heat loss in Vancouver. So 9C design temperature, 20-degree room temperature design. If we select the AH2A 213, we can get about 70,000 BTUs at about 180 degree Fahrenheit. So again, that sets our heating curve up to that 1.8, just like we had on the baseboard. And of course, we're going to hit dew point here at around +5 outside. Whereas if we selected the next size up air handler here, now we can start to basically reduce the supply temperature from 180 down to somewhere around 150 degrees, and to get the same amount of BTUs out of this out of the fan coil. But now you see that we actually are condensing right off the bat. So we're dropping that return temperature down below the dew point here, right at our design temperature. So instead of us, condensing, with about 70% of the heating season left to go, we are at 100% here. And the difference between these two these two units is only a couple $100 really, as far as wholesale cost. So as far as return on investment, you're definitely going to get your money back by selecting that large unit. There might be a bigger capital cost or outlay cost as far as materials here, but yeah, you're really thinking about that long-term efficiency of your system. It would actually go to a better, your system would be much more efficient with that bigger fan coil unit installed. So let's have a look at the different types of heat emitters that we're dealing with. I kind of looked at some high temperature ones there, baseboard. We also have like staple up type of system. So there's a radiant system that you would see in an in-joist type of heating. We have high mass radiant in-floor system here. And of course, when we operate these, they would all operate at different heating curves. They would require different supply water temperatures based on the temperature outside. And of course, these two graphs here are meant to kind of depict that. They're actually related. So there's your heating curves down here, and this is an efficiency graph at the top here. And of course, you've got your heating curves are selected here. So we've got your red heating curve down here is the 0.5 for the radiant in-floor system. The blue curve here is for the baseboard, fin tube baseboard. And the little green curve in here, an efficiency graph here, is for the staple up radiant in-floor system. The loads here. So when we talk about design temperature, that's when we talk about your maximum BT requirements will always be at your design temperature. So minus 20 degrees is the maximum, or basically the design temperature for the system, where we'd be at 100% of our load, so minus 20. And then the shoulder seasons, we're at 30% or less of the load of the boiler is going to be at the lower side of your heating curves here. So we start getting into more of the shoulder seasons, the spring, late spring, early fall, those types of things. And the boiler basically has a very small amount of load based on the 100%. So there's a relationship here is 100% minus 20, 30% in the shoulder seasons here, and the changing in the efficiency when we start using the heating curve. So you can see at 100% load, the baseboard system supplying 194 degree Fahrenheit is going to be somewhere around the mid 80, 85, 86% efficiency. The staple up in-floor system here is supplying at design temperature here about 167 degree Fahrenheit at 100% output. So it's again right around that 86, 85.5% as far as the efficiency goes. And the radiant system, the high mass radiant system is way up here at a 0.5. So it supplies at design about 104 degree Fahrenheit or 40 C water. And of course, a little bit lower as it gets warmer outside. But the change is very minimal in the high mass system here. So you can see it goes from about a 95% efficiency here. It jumps up to about 98.5%. So about a 3.5% difference in efficiency from design to shoulder season. Whereas if we use outdoor reset on a staple up system, we go from that, mid 85, 86% efficiency all the way up to about 97% in the shoulder seasons. And then, of course, the baseboard system, where we have that real high temperature here going out at design. And of course, as the temperature outside warms up, it drops down a bit, quite a bit here. So again, a very significant change in the overall efficiency of your system when you use outdoor reset on these higher temperature. So the radiant system here is really kind of the low-hanging fruit of your condensing technology. It's already below the dew point temperature, even at design. So as far as the efficiency change here, it's kind of minimal in comparison to the higher temperature systems or lower mass systems that we're dealing with. Not that it's there's no justification using outdoor reset on the high mass system. It's just that you have a greater impact if we start applying outdoor reset to these higher temperature, lower mass systems that we have available out there. And once we get these boilers to condense, it's kind of important to kind of look at, well, where's the energy savings going to be here? So in a shoulder season, when these boilers aren't firing very often, you don't have a lot of load on there, but the temperatures are quite low. The boilers are going to be condensing. You might get 3 or 4 gallons of condensate out of these boilers in a residential application, 125,000 BTUs. But that's about 32 cubic feet of natural gas savings per day. So do that for 15, 20 years in a system. That's a lot of energy savings during your heating season. Remember, there's over 6,000 hours of heating time that we're dealing with in some of these, these areas up north here. So there's, if we are doing this every day, that's a lot of energy savings that we're talking about, and we got to extrapolate that over a long period of time. At design, if we have systems where we've designed for low temperature, high mass systems like we looked at with that high mass rating system earlier, you could be up to 22 gallons of condensate per day coming out of those boilers. So, 178 cubic feet of natural gas savings per day at design temperature. So a large amount of energy basically that we can save if we make sure that these boilers are operating at the appropriate temperature, not overshooting what we need as far as supply temperature. So this is that graph I was talking about earlier. So we kind of give you some examples of where you want to kind of fit those curves, but ultimately it comes down to what your heat loss is and what your supply temperature requirement is based on the coldest day of the year in your particular area. And that's how you're going to pick the whatever slope you're going to be looking at here for operation. If you have a system here now that is, you can't add baseboard to, you can't select a different fan coil. All that stuff is already there. You're doing a retrofit. You're gonna look at some sort of outdoor reset strategy. How can we add efficiency to an already existing system with outdoor reset? Well, the curve is selected by the terminal unit, as we just mentioned. Your heat loss, the amount of area of surface area of heat emitter you have in there, and the density of it, high mass or low mass. But the heat curve does not select the delta T, so it doesn't select the difference between the supply going out and what's going to come back to the boiler. That is the engineered type of value here. And that delta T is actually part of that heat transfer equation. So when you look at heat transfer, how many BTUs we're sending out is going to be a function of the flow rate. How many gallons per minute of fluid flow do we have through the system? At a specific delta T from the supply to return, multiplied by a constant of the type of fluid that we're utilizing here. And if we change this variable, the delta T here, it's going to make changes to the other variables in the system here as well. And it'll come up with a new equation here, or basically a new gallon per minute flow rate if we change the delta T, or a change in the BTU per hour based on the difference in the change in the delta T here. So let's have a little example of what I'm talking about. So we see here, we got all the variables already figured out here. We're just going to throw them into this equation. You've got a 90,000 BTU an hour output right now from the heat source. We have a 9 gallon per minute flow rate going through our system, and we see we have 180 degree going out, 160 going back. So we got our delta T already figured out at 20 degrees. So we can throw these into the variables of our heat transfer equation here. And just a short definition of what this 500 is. It is the constant when we use water as the heat transfer fluid. So if it's not water, or not 100% water that we're utilizing as far as the heat transfer fluid moving through our system, then this constant here will be a different number. If you have glycol in the system, it's going to be a different number here based on your percentage of your glycol. So those numbers are available, but it really depends on, again, what we have here for heat transfer fluid. We're using water in this example, so we'll stick with 500. So throwing these variables in here now. So 9 gallon per minute multiplied by our delta T times the 500. We are going to get 90,000 BTUs as we work out the math here. But what if we decide to change the delta T here from 180, dropping it down to 130? It's possible if you wanted to. We could actually change the delta T here. There's nothing written in stone that we have to have a 20 degree delta T. This is basically engineered for what we're looking for. And the gallon per minute here, now we have to figure out what the change in the flow rate is going to be to give us essentially give us 90,000 BTUs at a 50 degree delta T versus a 20 degree delta T. So now we have the gallon per minute over on the left side of our equation. And now we're taking the BTUs and dividing it by the delta T times 500. So when we finish up the math here, we see now the flow rate will be about 3.5 gallons per minute at a 50 degree delta T to give us the 90,000 BTUs of heat exchange we need for the piece of baseboard here. Of course, that return temperature now is getting nice and close to what our dew point requirements are. So you can see that we can start to manipulate our delta T here, and we can start to drive the boiler into a condensing operation, even though we have a high temperature coming out, because again, everything is dictated as far as condensing as what's coming back to the boiler on the return side, and of course how it's going to pull that flue gas temperature down enough to get it into dew point. Is this possible with baseboard? Are the people going to be comfortable with this new delta T from 180 to 130? It really depends on how the baseboard is laid out, right? So if it's a big open area that you have that we're dealing with here, where the baseboard is in one large area, so it heats up a room en masse, then it is possible to play around and get some temperatures here. If it's baseboard that goes from room to room to room on one thermostat, what you have to be careful of here is as that water flows through one piece of baseboard into the next room and the next piece of baseboard, when it hits that last piece of baseboard in that last room, is that supply temperature coming in high enough that we're going to get enough BTUs coming out of that baseboard to heat that space effectively? So there is some challenges, obviously, that you have to deal with when you're talking about delta T's in different areas, but it is certainly worth investigating to see if we can start adjusting our delta T here to get our system into condensing much earlier. And again, the whole goal is that efficient heating system, and we can use that delta T to our advantage. Same thing with fan coils. Fan coil manufacturers, they give you correction factors for different delta T's that you can work with, different supply temperatures that you can deal with as far as BTUs. You can start to essentially look at different sized emitters here and do some different calculations to figure out which is going to be the best fit for the design temperature that you're looking for. And now, as long as we're, like I said, again, as long as we're getting the BTUs out of it at the right outlet temperature here to get our BTUs, then that building is going to be satisfied because we're replacing the BTUs that it's losing coming out the other side of the secondary side of that fan coil here. So we can use these low mass systems to our advantage to basically manipulate that delta T to get more of that heat out of it at a lower flow rate, again affecting the return temperature going back to our system. Again, a little bit more engineering has to be involved to get these systems to operate, but the goal here again is to get these boilers to condense as early as possible. Even if we're not in the condensing mode, as I mentioned, just dropping the supply temperature down is going to increase the efficiency of your heating system overall. A little rule in hydronics, the 3-to-1 rule. So for every 3 degree Fahrenheit, we drop the supply temperature going out. We're going to reduce the fuel consumption by about 1%. Think about your stack temperature. Remember, the lower the boiler temperature, the lower the stack temperature is going to be. So there's your savings right there. So there's some, add that into the 3-to-1 rule. Piping loss is the same thing. As far as that goes, your jacket loss, your stam, all those things basically start to improve as we have the boiler at a lower temperature versus a higher temperature. So just dropping that supply temperature down in your system, even if it's a non-condensing system, is going to add a lot of sensible efficiency to your heating system. So we're always basically, the whole idea here is that we want to meter out the exact amount of energy, which has a direct impact on that supply temperature going out. So if we overshoot that supply temperature, we're losing basically efficiency. So this kind of goes towards that whole idea of selecting the right temperature and not going over that temperature to satisfy your load. So how do we do that here in our systems? We're going to have a look at our boilers, our 200 and 300 level controls, effectively have the same logic to them as far as operations, whether it's a high mass boiler you see here, the CU3A, or the wall mount Vitodense 200 boiler, and the multiple sizes we have of those units. The control logic here is similar as far as how we treat the different zones. So if you have a one temperature system here, we have the HC1, so heating circuit 1, as we call it. We have a couple different ways of operating your different types of heating systems. We have zone circuits as well, but we're going to talk more about the heating circuits here in today's conversation. We also have heating circuit 2. So if I have one temperature here and I have another area of the building that requires a completely different temperature simultaneously, so it's going to require heat at the same time but at a different temperature, then I can actually add in some components here, and now I can have the boiler look at a second heating circuit. So there's HC2. And I can even add a third temperature to any of these boilers. So right out of the box, these boilers, you can add on some components and they will be able to basically start to expand the amount of temperatures your heating system can effectively operate without really going into a whole lot of complexity here. It's basically plug and play. And what you're going to add in here for different mixing valve or different mixing circuits will be the mixing valve extension kits that we have available. So you can add up to 2 of these to any one of our boilers in the 200 or 300 series. So you can have that high temperature going out without any mixing valve. And you can have 2 mixing valves added in basically to take that same temperature, throttle it down. And now we're dealing with lower supply temperatures going out to those emitters at the exact same point in time. So these little kits here basically have everything you need. You'll get a sensor that you're going to strap onto the supply pipe for that particular circuit to monitor its temperature. You have a mixing valve you're going to add into your system. You'll add the actuator onto the mixing valve and of course link the arm here to the mixing valve so it can drive that mixing valve open and closed. And this is the control that functions and communicates back to the boiler control, takes all the inputs for the sensors, as well as your pump outputs and the floating signal to the mixing valve are in this particular control as well. So this essentially allows us as a boiler to operate multiple system controls, and each one of these circuits now has its own heating curve. So now as we operate, these are at 3 completely different reset temperatures simultaneously. And in comparison to doing this with thermostatic mixing valves, so pulling these off and just throwing thermostatic mixing valves in, the big difference is these are going to be about 5 to 6% probably on average per year more efficient as far as operation than a thermostatic mixing valve would be in the exact same application here. Because thermostatic mixing valves actually don't do anything other than put a ceiling, just cap the max temperature going out to these zones. They don't actually adjust and manipulate the supply temperature when it's in a lower temperature capability. So as long as these systems are in operation, these valves are going to keep this system on a heating curve. Whereas if these are thermostatic mixing valves, basically we would follow the one heating curve for the high temperature until the temperature got so hot coming out to this that the thermostatic mixing valve would actually throttle that back and make some return temperature to it. So it's not really a true reset type of component. So when you add Viessmann mixing valves to your control, we do have a differential that is between the boiler and these mixing valves. And I'm going to explain why we have this adjustable differential here. It's usually set to 8 degrees Celsius or 8 Kelvin. And the reason why we have a differential of that temperature in comparison to what the mix, because we have a mixing valve in there, why not have the no differential? Why not send out the exact amount of supply temperature that mixing valve, and basically so we can have a temperature spot on to what we're looking for. Well, the mixing valve does that automatically. So it basically, the control arm is going to adjust that mixing valve so that we have precisely the amount of return water mixing with the supply water. So we oftentimes are spot on with the set point that we're looking to go out to the system, but typically, maybe 1 degree off, or as it's operating at 2 degrees. But, even when it's adjusting, it's only very small incremental temperatures it's off and differential. What the differential on the boiler side allows that mixing valve to do is kind of stay in about the 50% position here. So it has more controllability. So if there's little adjustments it has to make, the valve isn't sitting all the ways over to one side. So if we had this differential set to 1, then you'd have your valve basically operating all the ways over to one side all the time, right? So not mixing really a lot of any return water with the system. But as soon as there was a change, and all of a sudden we had the mixing valve to make an adjustment, we would really have to make some real severe hunting adjustments to basically find that new control set point. If we keep that differential in the control, and this is part of our coding, 9F, 8, if we keep that differential in there, the boiler is allowed to operate a little bit longer. So you get those longer run cycles because the boiler is in that differential range. But the valve also tends to stay in this position. And if it has to make any incremental adjustments, it's just going to swing slightly to one way or the other to maintain that set point that we're trying to get out here. So again, nice and efficient as it operates. And of course, the boiler now gets a slightly longer runtime at that little slightly higher differential. So it basically helps to make sure everything is in a good control authority as it moves through the heating season. So that's some addresses in there that we have related to mixing valves. Also, when you use mixing valves, you have the ability of what we call a reduced priority application, which means that in a domestic hot water, so when we're talking about priorities, it's usually the domestic hot water is requiring heat. So we turn the heating system off, shut the pumps off, close the mixing valves while it's in operation, and we completely heat the tank. Once the tank is satisfied, all the pumps are allowed to come back on, the mixing valves are allowed to open. Well, with this address A2 in your encoding level 2 of your Viessmann 200 and Viessmann boilers, you can actually program in a reduced priority level here. And what that essentially means is that the boiler control is going to look at, and this is just different, every day. It depends on what the temperature is outside, how easily the tank is being heated. Is it catching up to the tank recovery? As long as it's not going to impact the recovery of the tank, it will actually open the valves and turn the pumps back on here at a reduced level, or maybe at full operating capacity. It just depends on the state or at that particular point in time. So if you look at a system here, you think about systems where there was no upsizing of the boiler with the domestic hot water and, maybe some small commercial systems or something like that, where this could be advantageous, where we keep the system operating maybe at a reduced rate while we're doing domestic. So it doesn't really pull the temperature of the building down all that much as it's doing domestic hot water. Or if you have recirc loops, a lot of recirc loops out there that are running 24/7, you get a lot of cycling of the tank, especially if those lines aren't insulated on the recirc side. And of course, this will allow you the system to still operate those heating systems at possibly reduced capacity. So a really big advantage actually to utilizing the Viessmann mixing valves in these types of systems as well. So it gives you some real control flexibility to essentially make sure that that system is operating not just on an efficient level, but also keeping the occupants comfortable as we are going through this heating season. Now, what if you wanted to turn these pumps off? So it's always been one of these things with heating circuits. These pumps run 24/7. It's all about that keep up versus catching up. If you've taken in some of our previous seminars, whether you've been in class here or some of the online stuff that we've been providing, you always have the ability of starting and stopping these pumps. With heating circuits, it's about, typically, are these pumps required to start and stop? So do they have to stop because as all the zones are closed? If they're of a variety of pump that they need to stop, so not a variable speed type of pump that slows down based on pressure differentials, et cetera, which don't really have to stop when the zones are closed. But if you have, fixed 3-speed pumps, or you've taken pumps and put them on some sort of, fixed flow or fixed pressure differential, then you may have to start and stop those pumps when these zones aren't calling anymore. We have that ability for all these heating circuits. So if you had 3 different temperatures, you had 3 different pumps we had to control here, we can easily do that with utilizing our little EA1 module that comes with every one of these boilers. So the Viessmann 300 as well as the Viessmann 200 boilers have these controls in them. And these little contacts on the left-hand side here, DE1, DE2, and DE3, act like in-switch contacts, like TT contacts you would see on a traditional, aquastat or relay box or something like that. And you can program these using the coding level 2. Address 3A programs DE1, and there's a bunch of different capabilities of programming these. So when we close this contact, an in-switch closes here, what's this shorted contact or closed contact going to tell the boiler to do? If we put 3A to 1, it's a change in heating program. And what that does essentially is when we close the contact, and when we do some programming adjustments here, we're going to tell the control that we need to heat that particular heating circuit. If we have a second heating circuit, we can take the in switches for that temperature, and we could take that to DE2 contacts and do the exact same thing. Take address 3B and change it to 1. If we have a third temperature, a second mixing valve in there, we can do the same thing with those zone valve end switches and take those to the DE3 contact here on 1 and 2 and make the adjustment here on 3C. Then there's a couple of programming adjustments to make. We want to be able to tell the control that when I close that contact on 3A, B, or C, this is what the control is going to do, and this is how we program it in D5. We change it to 1 for continuous operation in normal control mode. And then, of course, we want to program the contact. So if I want DE1 to be associated with heating circuit 1, then I change D8 to 1. If I wanted DE2 to control heating circuit 2, I take heating circuit 2 and I make sure that D8 is 2. And the same for DE3. If it's going to control the heating circuit 3, then D8 would be at a value of 3. So then basically, and there's a couple other coding addresses in there, a couple of timer adjustments to make. But effectively what you do here now is you will start and stop that pump whenever the zone valves open and close in those different heating circuits. And the other advantage is that if the high temperature circuit here is not calling, but one of the lower temperature circuits are calling, the boiler fires to that particular set point. It doesn't go to the higher temperature set point of the high temperature loop. So it differentiates the temperature settings based on what particular load is calling as well. So you get a little bit of advantage there. Not much, but generally speaking, your lower mass systems cycle way more than the higher mass systems are going to anyway. So more often than not, on average, if you have a baseboard system, those zone valves will be, thermostats will be calling a lot more. So the DE1 here would be calling a lot more than the other zones would be to begin with. So we have the different temperatures we're dealing with. And as I mentioned, if you have 3 temperatures in your system with a Viessmann control, you can operate 3 different heating curves. That would mean setting up the 3 different heating curve parameters for each one of those circuits. And the parameters are the slope, the shift, and of course the room temperature set point. And we use these 3 to give us the ability to actually to take a standard heating curve and customize it to the building that you've installed this boiler into. So every curve is generic. It's not specific to your building. You make it as the technician, as the engineer, you customize that heating curve to the building that you're doing. So every occupant's a bit different from your, the previous customer that you had before. That building is going to lose heat at a different rate than the other buildings. Of course, it requires us to do a little bit more than just select the heating curve, although that's a lot of what's done out there. A lot of times we go to systems that have been operating for years. The heating curve has never been changed from the default. There's no slope, no shift, no room temperature adjustments. The people are comfortable in the building, but there most likely is some money being left on the table there as far as that efficient heating system that we're losing out on. So the slope is what we select during the commissioning side of it. So basically it's if we want to maintain a 20-degree room temperature inside and our design temperature is minus 20, then of course we see here that we want to maintain about 160 degrees or so supply temperature, or sorry, 75 degrees supply temperature at minus 20. We're going to pick that 1.4 heating curve, and that's going to basically commission our system. We're going to start off with that, and it's going to allow the boiler now to follow this curve. So we get exactly what we're looking for at design, but as the temperature outside changes, the curve is basically going to adjust that supply temperature accordingly. And then the system has to go through some operational times here. If that's all you have for information is that one temperature at the design, then of course, we're not really sure just how effective the rest of the heating curve is going to be. The occupants most likely are going to tell you as they go through the heating system whether they're comfortable or not. Generally speaking, if the temperature is too cold in the building, that's when you get the phone call. If the supply temperature is too warm, oftentimes you don't know that because the thermostat's going to cut that supply temperature off to maintain a comfortable room temperature. But there is going to be some money left on the table there. So let's look to see how we can kind of manipulate that as well. So this is a slope. With shift, what you have here is the ability to make some incremental temperature adjustments right across the heating curve in a parallel type of configuration. So you see here that there's the old heating curve that we just looked at with the different supply temperatures, the 5 that we outline in the graph when you look at the boiler control at a 1.4 heating curve. Now I've taken that same curve and I've taken the shift up 10 Kelvin, 10 degrees C. And you can see that previously we had 20 degrees, now we're at 30 degrees. 37 degrees at 10, now we're at 47, 75 at minus 20, now we're at 85 at minus 20. You can see what happened here is every temperature went up 10 degrees. So effectively that curve just shot up on a parallel scale here, 10 degrees right across the board. Often what I do with the shift, as far as trying to get the system in efficiency, is if there's been no complaints with that old heating curve, if the slope is at 1.4, and I, ask the occupants, after a year of operation, they say, no, if everything's been nice and comfortable, I'll go to the shift here and I'll drop it down. Actually take it down maybe a degree or two. And remember that whole 3-to-1 rule. So for every 3 degrees I drop it, there's a fuel savings. Also the ability maybe of getting the boiler to condense a little bit earlier. So we're going to start to get into some more efficiencies a bit earlier as far as the system here. And what we're trying to do here is essentially affect the supply water temperature as it comes out without affecting the occupant's comfort level. So they only know what the thermostat told them. They don't know what the supply temperature was. We're going to start to manipulate the supply temperature by dropping the shift down a couple degrees if everybody was happy the year before, and then seeing if there is no complaint. So effectively what you do is you keep dropping that until you start getting a complaint, and now you've actually got the spot where that curve has started to be configured for the actual heat loss of that particular building. The other side of it is the room temperature set point. So slope is one thing, shift is another one. We can manipulate those to customize that curve. The other area here is the room temperature we deal with. Now, this temperature is often difficult to explain when we have people coming into class. The boiler actually has no idea what the indoor temperature is. There's no sensor unless you actually supply an indoor sensor that we do have available. That's for another day. But as far as the one that's on the boiler, that room temperature set point that you program on the boiler, it's a nominal value. You're telling the boiler this is a target for the building. It's also the warm weather shutdown point. So once the temperature outside gets to a certain level above this, the system's going to go into a warm weather shutdown, turn the pump off, close the mixing valve, and no more heat being delivered. But what happens if I adjust that room temperature set point? So what happens is all the curves that were pinned or anchored to that original room temperature now all moved over to the new setting. So I went from 20 to 25. So if I did that on my control with a 1.4 heating curve, you can see that at an outdoor temperature of 0 degrees, 32 Fahrenheit, with the old curve at 20 degrees C, we had a 50 degree C supply temperature, 122 Fahrenheit. With the new room temperature adjustment, it goes up above 60 degrees. So a 5 degree temperature change here equated to a fairly significant change in supply water temperature as well. So there is, there is an adjustment here, but not like a shift where it was incremental, 5 degrees goes 5 degrees. This all depends on the angle or basically the slope of the curve that you selected, just to what degree this change is going to, how drastic the supply temperature change is going to be is really based on the slope of the curve that you've selected. So the steeper the curve, the more dramatic this change is going to be when we start making adjustments to the room temperature here. It also adjusts the warm weather shutdown temperature we're going to see here in a bit. But what this allows us to do now with these three different functions, and this kind of gets towards being able to manipulate these curves specific to your application. You can start off with the heating curves we talked about. As I mentioned, they go through a year of heating, and all of a sudden, you go back and the people are saying during the heating season, not a problem. When it was cold outside, we were comfortable in the building. But during the shoulder seasons, we had some issues keeping maintaining the temperature. This is basically what you could do with these variables, these three different parameters, is you start customizing this heating curve. So we know that shifting, we could boost the temperature by shifting the heating curve. So we could do that. That's going to satisfy that shoulder season, increase the supply temperature. But now we're not efficient anymore because we're overshooting supply temperature during the design temperature, which was fine with the previous heating curve. So if I take the slope and drop it down and boost the shift up, what I've done now is I've got a brand new heating curve. So a little bit flatter, and now it compensates for the shortfall of the original heating curve in the shoulder seasons without overshooting and making this system, again, as efficient as possible, but with comfort level as the primary focus of the system here. The other thing you can do with our curves is that not every terminal unit is going to work very well coming out of warm weather shutdown at a low temperature. So think about a fan coil. You don't want to, don't want to be blowing around 20 degree or 68 Fahrenheit air in a fan coil. That's going to be very drafty and probably uncomfortable. You might have to set a minimum temperature for your baseboard or for your fan coils coming out of warm weather shutdown, where we need to say, we need 122 degree Fahrenheit supply temperature, or we're not going to be able to heat the building effectively. Maybe you've got some long pipe runs that aren't insulated, and of course, if it's anything lower than that, we don't get the radiator temperature that we're looking for, hitting the emitters at the right temperature. So that you set this minimum temperature, and we can also set a max temperature, basically to help prevent any type of overheating of different types of units. High mass radiant systems, for instance, maybe cast iron radiation, where you want to lower that set point temperature down a bit so it doesn't, that you don't have any real hot rads out there. These are all programmable in your heating circuit area as well of your of these 200, 300 level controls. We can set a minimum temperature to start off with and a maximum temperature. So you can see what happens here. If I set a minimum temperature, the boiler basically fires to that set point until the temperature outside says it needs to go higher. So you still have a heating curve in here in the blue, but we basically put a floor and a ceiling on that heating curve for specific reasons to make sure that we heat adequately, but we don't overheat. And we put a little governor on the top end as well. So these are all programmable. As we talked about, your efficient heating system is all about basically replacing the energy that we're losing in the building. So shouldn't the quality of construction of that building be part of the strategy in your outdoor reset control? The Vitodens 200 and the Vitocrossal 300 control have this little address. This address 90 is an averaging of the outdoor temperature. So the idea here is that if you have a really well constructed building, if we average the time over a longer, stretch it over a longer period of time, there's going to be less fluctuations happening. And that means that the temperature adjustments will be less. And that will mean that you've got a much smoother operation of your boiler versus a poorly constructed building, where you might have to basically ensure that basically the boiler reacts a bit quicker to the outdoor temperature. Otherwise, we're going to have some issues trying to heat those poorly insulated or poorly constructed buildings because the boiler supply temperature is not keeping up with the actual heat loss of the building. So we use this time constant here. It's always set to a safe spot here where it's not really going to be a problem. But as a contractor, as an engineer, you have the ability of looking at the different types of quality of construction here and manipulating this value to essentially ensure that we get the best type of operation out of that outdoor reset system. And you'll see in our controls, you have this dampened outdoor temperature. And we're going to try to explain what that dampened outdoor temperature actually means here. So as we go through our control, dampened outdoor temperature is that averaging of this time constant. So we look at it in the address 90 at 36. It's a 6-hour average of the outdoor temperature that you see here. And the boiler is going to take that dampened temperature, the boiler control, add it to the actual temperature, divide by 2, and it's going to use the average temperature here as far as the utilizing the outdoor reset curve. So as far as the value for outdoor reset, it's a 10.5 degrees C outdoor temperature, not a 10 degree or not 11 degree temperature here. So it does have a direct impact. And of course, the longer the averaging, the essentially the less fluctuations you're going to have in that temperature, which means the essentially a much smoother operation of your boiler set point. So again, the more efficient the building is, we want to reward that efficiency by ensuring that the control understands that, it's going to take an awful long time for that building to cool down because it's well insulated. So we can average that temperature out a much longer time frame. So that's available in our controls. And as well, as far as outdoor, warm weather shutdown, in your coding level 2, address A5 is your address to look at here. It's already defaulted to 5 as a value, which means that when the temperature outside gets 1 degree Celsius or 1 Kelvin above your room temperature set point, so this case it's 20. So once we get to 21 degrees outside,
the control is going to turn the pump off, and then it's going to shut the mixing valve off if there's a mixing valve attached to it. And that's basically when we go into warm weather shutdown. When the temperature basically drops down below the 20 degrees, we're going to go back into basically heating operation. The pump will turn on, and the set point would be given to the boiler to operate to whatever it needs to satisfy the load here. So there's your warm weather shutdown, and it's basically adjustable to a bunch of different variables here, as you can see, depending on what you're looking at. We also have time programs. So, you just like your programmable thermostats you have in buildings where you set the, night setback for bedrooms, and maybe during the day when nobody's home, you drop the temperature with your thermostats. That's great. You're just adjusting air temperature in those particular thermostats. It doesn't influence the actual supply water temperature of the boiler. And that's where the energy savings is. If we can actually turn the temperature of the boiler down going out, it's going to make a bigger difference as far as energy savings goes here. And so these are, meant, they're in there. They have 4 on-off periods per day per heating circuit. So if you have 3 heating circuits, you have 3 different timer programs you can adjust here. And the idea here is that, some type of heat emitters you may not want to use, high mass radiant inflow systems, for instance. You have troubles with the mass and the flywheel effect of the concrete, where it basically leads and lags as far as the adjustment of temperature. But certainly in things like fan coils and high temperature baseboards, et cetera, you could utilize these timer programs and really start to extract some efficiency out of these boilers by putting them on the same type of schedule you would with a regular old thermostat. And this is how this is going to work. So as we have, when we have a night setback, what we're going to tell the control is we have a temperature during the day we want to achieve, or during occupied times, and we have another temperature that we're going to drop to when when nobody's in the building, or when we're all asleep. And the difference here is, the warm weather shutdown temperature is going to change. So now if we set this to 14, it's a little bit dramatic, but say 14 degrees indoor temperature from 20 degrees during the day. Then if it's above 14 outside at the evening, it's actually the system will go into warm weather shutdown and basically keep the building, because we only want 14 degrees, it doesn't need to heat the building anymore. But even if it's below 14 degrees outside during a night setback here, if we had left the control in normal operation, we would have been targeting 50 degrees, but because we set the temperature back at night, we dropped down to 37 degree Celsius supply temperature in the evening. So there is your 3-to-1 rule in application, but also a much different latent heat recovery out of the flue gas as well when the burner fires because of that lower temperature. So a much more efficient combustion is going to happen as well. So more energy savings by using the devices that are already built into these controls. There's already some programming that we have built in the controls as well for operation. So when we go into your heating circuits, some people would worry about, well, night setback's great, but what about that pickup factor in the morning? So we drop back, at 10 o'clock at night, and the control stays, basically in a lower temperature until 6 o'clock in the morning. And then all of a sudden we have to pull that temperature of that building up from our night setback. There is a logic that's already in our coding, which is already pre-configured, which will effectively ensure that we don't have such a large pickup factor in the morning on the buildings. And how it does that is it monitors the outdoor temperature, and it starts to pull the control out of night setback if the temperature starts to get extremely cold. You can manipulate these values, but they already preset. F8 here basically is a starting point for terminating the reduced mode. So at -5, you can see the heating curve is adjusting, but at -5, instead of continuing on here, it starts to basically ramp up the supply temperature until it reaches -14 outside. You can see what happens here is we go from our night setback heating curve to our normal daytime heating curve once we hit about -14 outside. So the idea here is that if it starts getting really cold outside, we're not going to stay in night setback. We're going to allow that to control, basically to pull out a night setback so we don't have such a large pickup factor. If we have basically on the other side, if we want to boost that temperature, so when we come out of night setback, we want to basically raise that set point for a period of time just to speed the recovery of the system as far as the room temperature and comfort level. We want to speed it up a bit. You have 2 more addresses, FA which is the percentage of raising that set point temperature. So we could say by default it's at 20, which means that we're going to raise the temperature by 20% during that boost period to basically speed up the recovery of the heating system. And how long are we going to boost that temperature up is a function of the FB address here of 60 minutes. So basically what this tells you is for 60 minutes, we can boost the temperature by 20% to basically speed up the recovery of our building when it comes out of night setback. So these are all part of the control. They're built into all these controls. There's nothing special. It comes out of the box and it's ready for you. We also have a holiday program. So when the young fella goes down to Vegas to play blackjack with his family, they can put their system into a holiday program here. And basically, when they leave, the system goes into basically a setback period. When the day they come back, it heats the tank back up for domestic. The temperature in the building comes back. So there's some energy savings during that vacation period that the occupants are going to realize by not heating the building to the normal operation. So all those things are part of our control that we offer you, and that all that stuff is meant to basically, if you don't use it, it's in an area where it's pretty safe as far as it's not going to influence any operation. But if you start utilizing some of those addresses and tweaking things, you can really start to customize these buildings for energy savings and make sure that you're getting every bit of energy that you can out of that cubic foot of gas that you're burning. The other side of it is how we pipe the boilers. And of course, manufacturers give you a boiler. The system itself has as much impact on how well that boiler is going to fire as anything else. So we look at, what is a high mass boiler versus a low mass boiler. It really doesn't have anything to do with the BTUs. The BTUs here, you see, we have a 199,000 BTU 200 boiler, 199,000 BTU CU3A boiler here. The difference is in the weight. So the mass of the boiler, bigger boilers, heavier metal. When that burner fires, it has to heat all that metal as well, in that boiler. The water content in the boiler as well, under 4 gallons of water in a low mass boiler, almost 19 gallons of water in a high mass boiler here. So when that burner fires, you got lots more mass there that's going to absorb the temperature there. So as far as operation, we're not going to cycle as often in a high mass boiler. And all those things go towards how we should pipe these units. So we saw a little bit of the 3 little pigs earlier in one slide, and now we're going to change into into Shakespeare here. And what does Shakespeare say about piping? Is talk about this whole primary secondary side of boilers. That's where it comes down to high mass versus low mass. When does separating the boiler from the heating system become something that would be desirable? It adds cost, obviously, to your system. You're adding a pump. You're adding a bit more installation time for the T's and all that kind of stuff. But there is definitely some value in here as far as operation of the boilers. As a boiler manufacturer, obviously, we'd sell more boilers to you probably if we said, just hook it up directly to the heating zones and away you go. Don't worry about primary, secondary. The boiler's going to fire without a problem. Well, that's true. Probably would. But would it fire as efficiently as a boiler that's piped primary, secondary? That really comes down to the question here: to pipe or not to pipe. Is the boiler going to operate more efficiently with primary, secondary, or is it basically essentially not going to add a lot of value to that system because it really didn't need to be piped to primary, secondary? Let's have a look at the factors that we want to look at here to determine what we want to do. The first thing comes down to the type of boiler. So we have a water tubed heat exchanger here in the Vito Dens boiler here, and pressure drop is a consideration through the heat exchanger itself. So if I had a couple of pressure gauges here and I was pushing water through this heat exchanger, the same B2HB 160, so looked at that one we just looked at that was on the scale there, its maximum flow rate is about 14.3 gallons a minute. So usually low mass boilers will have that kind of tag on them, the maximum flow rate. So we don't want to go any higher than this. You go any higher than this, you might have velocity issues, noise issues in the boiler. We like to keep the number at a maximum here. So 14.3, you see that the pressure drop at 14.3 gallons a minute is about 21 feet of head. So a substantial amount of the energy of that pump is basically pumping fluid through here. A lot of the pressure drop or head pressure capacity of the pump is used up just by pushing water through the heat exchanger. Same thing in a commercial B2HA 399 or 530. It has a much higher flow rate, maximum about 38 gallons a minute, but the heat exchanger there is going to absorb about 15.7 feet of the head capacity of the circulator, moving that water around that heat exchanger. By comparison, let's look at a high mass boiler here. So this is the Viessmann CU3A. So there's the heat exchanger, and there are the pressure drop curves for the different sizes. We look at the flow rates. So the 94 to 125, if we want to maintain 94,000 BTUs at a 20-degree delta T, we need about a 9.9 gallon per minute flow rate. On a 125 to maintain 125,000 BTUs at a 20-degree temperature drop, we need to flow 13.3 gallons a minute. You get the idea. 160,000 BTUs, 17 gallons a minute. 199,000 BTUs, 22.7 gallons a minute. What are the pressure drops? At 9.9 gallons a minute, you're at about 9 inches, a little over 9 inches, not even a foot of pressure drop at that flow rate. At 13.3 for the 125, you're up just over a pound or 1 foot ahead. So not even a PSI yet of pressure drop. For the larger boilers at the 17 gallon a minute flow rate, you're at about 11 inches, so not even a foot of pressure drop yet. And we're at about just under 20 inches of pressure drop at 22.7 gallons a minute, rowing through a SU3A 199. So you see here that we're not even at a PSI of pressure drop at these different flow rates. So really, as far as the calculation, they barely eat up any of that pump head capacity. So right away, there's a difference there. We can use basically smaller pumps on these heat exchangers and get without the pressure drop being an issue. The other side of it is how the boilers react, and this is more about low mass versus high mass versus heat exchanger design. But what about directly coupling low mass boilers to zones? And this is where kind of the problem really starts to kind of engage in. As the boiler is firing up, and of course zone valves are opening here, when we size this pump, we sized it for all of these zones to be open. So now we have 4 zones open. We're at design flow rate here right now. So the boiler's basically got the design flow rate going through it, the design flow rate going through the system, and design pressure drop. And now you start shutting zones off. So if we're not at 100% of those zones open, we really don't know what the flow rate is. And as we change the flow rate through a low mass boiler, you got to think that there's a small amount of fluid in these boilers. And as we change that flow rate, the temperature rise across the boiler is going to change. The boiler is going to pick that up as a change in load. And of course, if we are close to that boiler firing and it's getting close to its set point, if you look at here, if we have a small change in that flow rate and that burner hits that set point, it's going to stop that boiler from firing, and it's going to come right back on again as that temperature drops in the heat exchanger. So that's a cycle that's undesirable. And even with the highest turn down ratios, if these burners are in operation with multiple zones, it's going to be a real challenge for that burner not to cycle during those shoulder seasons, in particular when we're not at design temperature. So it's not desirable for your low mass boilers to have a single pump operation like this where they're coupled to multiple zones, because that is definitely going to adjust the flow rate through the boiler. And the potential there is for cycling, which leads to essentially inefficiency as that burner turns on and off. That's when we start getting into consumption of gas. More components basically being changed over the life cycle of the boiler. So more, igniters and more ignition modules, more issues like that as those controls go through their cycle. So not desirable. And that's where primary secondary comes into our system. So when we have low mass boilers, we have multiple zones attached to our system here, it's desirable to decouple that boiler from those zones, allow the system pump to deal with the pressure drop through the heating system, allow this boiler here to deal with the pressure drop through the boiler, but nothing on this side changes the flow rate of this pump. So as this boiler fires, it always has the same flow rate, allowing the burner now to modulate as it wants to its set point. So a couple of rules here when you're piping this with closely spaced tees. The idea behind this, there's really not a lot of magic. The only thing you have to really remember here is that we turn on a pump here. So our boiler pump here is now running. You'll notice that as the fluid's pushing through this system, that it's not moving into the secondary side of the system. As the water flows through here, if we were to put pressure gauges here, it's important that there is no change in pressure between these 2 points. If there's no change in pressure between these 2 points, the fluid moving across here does not see these as branches. It just essentially sees this as a straight run of pipe. So this little area in the middle is the common piping. So when I change the flow rate here now to this pump coming on, you'll see that the common pipe still has flow through it, but now there's no water moving up into the branches on the boiler side here. It's moving right through, right across, and right through the system here. When you see a zero pressure differential here between your gauges, the water will not see, or fluid's not going to see a pressure differential. It just sees a straight run of pipe here, and there's no advantage for the water to move in this direction because it basically doesn't see any differential pressure between the two T's. It's just going to basically operate as if this was just a straight run of pipe. So the desire with primary secondary is we reduce the pressure differential between the T's to zero. And that's the idea behind the distancing. So the wider the distance between the T's, of course, we put a pressure gauge in there, you're going to actually start to see a pressure differential. And that's when you're going to start getting some of this fluid now moving up into areas where we don't want flow to be. So keep that pressure differential at zero, and that's going to be successful in your primary secondary. The other option is using, these are named a bunch of things. Viessmann, we call it a low loss header. So primary, secondary headers, another one. You might see hydraulic separator out there. Effectively, they all do the same thing. The idea is that instead of closely spaced T's, you decouple the boiler side from the system side using essentially these devices here, these components. And when the water hits these devices, they're usually often 4 or 5 pipe diameters larger than the piping connected to it. The water slows right down. And often what you get is what we call laminar flow. And same idea, if you put a pressure gauge between this area here and this T down here, there would be zero difference in pressure. Same on this side, a pressure gauge here and here would be 0 PSI pressure drop between these two T's. Therefore, the water, when it moves through, if this pump is not running on the system side, we're just going to get flow directly back to the boiler without any flow moving out into the system here. Some other things that these devices add is they're also air separators. So they, because of essentially the physics of it is very similar to how an air separator works. You put a air separator in there. There are larger pipe diameters in the pipe and we connect it to. The velocity of the fluid flow slows down. When the velocity of the fluid slows down, the air basically microbubbles, the air escape. And in the case of your low loss headers, the bubbles move up the top of the header, and of course the fluid keeps on flowing. So we trap the air in the primary secondary header. Some of them have air vents at the top that move out. Some of them are manual, some of them are automatic, but they are basically act as an air separator. Some of the inspectors in our locale in Vancouver here will actually accept this as an air separating device. So you wouldn't need an air separator in your system if you put a low loss header in. So you can take the money that you have in that device and add it to this. That gives you some more value. It also adds some mass. You got some water in here, so a good chunk of water in here. Any additional mass helps a low mass boiler continue to operate. And some of these manufacturers, you can add dirt separation as well. So something we can add magnets to, et cetera, to increase the amount of dirt separation to clean up those systems as well. So there's a lot of value added in those. But when you add primary, secondary to your system, you also have 3 potential conditions that could be happening depending on the time of year and the flow rates in the system. So you have the first one here. You can see where the flow rate is on the boiler side is the same as the flow rate on the system side. And when that happens, the flow rate basically goes straight through the header and goes right out to your heating system. Return goes straight back from the system right back into the boiler. Nothing happens in the low loss header itself or the primary secondary header. It's just a piece of common piping. That's it. You could also have in the shoulder seasons when you have lower flow rates on the secondary side, so maybe just a zone open that's calling for heat, and the boiler is operating at full, full pumping output here, where you got more of the fluid supply from the boiler bypassing around and coming back into return. So what we're doing is we're elevating the return temperature with that boiler supply water temperature here. Or during the design or during the heating season, typically what you see is the boiler flow rate is lower than the system flow rate. And now you have the reverse of this second example where we got more return water coming back from the system, bypassing and going up and mixing with the supply water coming from the boiler to give us a temperature coming out to the system here. So let's examine these three different, or these different applications. And it's important here that the boilers know what's going on in order to control this. So if we're in a time of year where the boiler is flowing at 6 gallons a minute, but your system is at a high load capacity here, so it is maybe design day here where we got 10 gallons a minute of flow rate on this side. What happens here is 6 gallons a minute coming from the boiler, 10 gallons a minute coming back from the system. We can't have 10 gallons a minute coming back to the system. All that can't come back to the boiler. We have to have 6 gallons a minute out, 6 gallons a minute back, 10 gallons a minute out, 10 gallons a minute coming back to the system. So what happens at the header here is when the return comes back from the system, 6 gallons a minute goes this way, basically to give us 6 gallons a minute of flow on the primary side. 4 gallons of that return water bypasses and mixes with your boiler 6 gallons a minute to give us our 10 gallons a minute out. When that happens, you can see with this little equation, you can work out that this temperature now coming out to our system is not 130 anymore. It's mixed down to about 114 degrees Fahrenheit here. And if your boiler doesn't know that this temperature is too low, how are we going to be able to make sure that that temperature is what we're looking for? Oftentimes, if the boiler doesn't know that, we need some other control to say, hey, you got to pick up here and supply a hotter temperature here. Or the control logic here is just to overshoot and go to some set point to make sure that we get the right temperature going out here, or at least minimal temperature. Viessmann does it with a sensor. So every boiler that you get when you pipe it primary, secondary, we call it a low loss header sensor. More appropriately, it's actually a secondary supply temperature sensor. So when you do primary, secondary, this sensor is meant to be used to pick up the temperature actually going out of T3 here to make sure that we get the right temperature. So if we have 114 going out, we're not going to satisfy the load here, and you're going to get complaints of system temperature. If the boiler has no clue what this temperature is and it's just overshooting to supply a temperature, then obviously we're not efficient in operation. When I take a sensor and feed this back to the boiler, it now looks at this temperature and says, don't worry so much about what the boiler is. I got to make sure that this temperature here is correct going out to my system. I need 130 going out to the system here. So what the control will do is, with the feedback of a low loss header sensor to the control, it actually has a little algorithm here where it says the boiler set point temperature is going to be a function of the desired supply temperature, in this case 130. Added to that, the desired supply temperature subtracted by the actual temperature. So we see that we're about 16 degrees off. We have 114, we want 130. We're going to add that 16 degrees to the boiler set point. So in this system, our boiler, a 200 or 300 pipe primary secondary, would be firing at 146 to maintain 130 degree Fahrenheit temperature here. So basically giving you precisely what you're looking for on the secondary side without overfiring that primary to a temperature just to achieve what we're looking for here. So control of that temperature, again, is what we're trying to achieve. Again, if we have the opposite, so this is, again, an issue with primary secondary, is we might have a time of year where the system flow rate is lower than the boiler flow rate. You've got 4 gallons a minute on the secondary, 6 gallons a minute here on the primary. Now we've got 2 gallons a minute bypassing back to the boiler return here, elevating that return temperature from what we're coming out here. So we're influencing this return temperature now and bringing it up to a temperature which basically reduces the efficiency of the boiler. Now remember, Viessmann's boiler and the Vito Crossa boilers, the boiler sensor now coupled with the low loss header sensor can pick up what these two temperatures are. And if the boiler sees this, what it's going to do is it's going to keep that burner in low fire. So again, trying to keep the burner running as long as possible. And of course, adjusting the set point here, knowing that it doesn't need to fire any higher because the low loss header, the actual supply temperature set point here is already being achieved, right, with that lower load that we're looking at. So again, the logic in the boiler, the whole idea here is whether it's primary, secondary or not, is to try to keep this boiler running as long as possible. And using that sensor here in this particular time of year is going to be advantageous because we're going to reduce the cycling times of the boilers, keeping them in low fire, and of course, increase in the efficiency of that boiler because it's staying in a low fire condition. And so we've basically looking at this primary, secondary, not really required on the high mass boilers that we're looking at, the CU3As, you know, as in a standalone application. More appropriate when you start using multiple zones that you add those to your low mass boilers. Will a low mass boiler work without primary, secondary? Yes, they do. You've seen them out there. This boiler is working. What's Scott talking about having to put primary, secondary on these boilers, but are they as efficient, you know, through the life cycle of that unit as they would be if they had primary, secondary added? So that's what the really where the details are in. Sure, we like to sell you boilers, but we want to tell you the right information here to make sure that you understand what's a better system, what makes a better system versus, you know, what basically doesn't add any value. So with a CU3A, you know, standard piping, we got the dampening effect of the high mass. With this low mass boiler, we want to make sure that we keep that constant flow in that secondary or primary side when these zone valves over this way are operating and opening. Finally, thank you guys for hanging with me here. I know I'm droning on here, but we're just about finished. Maintenance of your boilers. So servicing your low mass boilers in operation here, those boilers are small. You know, you grab them, you know, off the back of your truck, you hang them on the wall, you vent them. Those are small flue gas passageways. Any low mass boiler, those flue gas passageways have been dramatically reduced from a high mass boiler. And of course, they require preventative maintenance, right? Anything that we're burning carbon in, you're going to have deposits. And of course, the longer those deposits stay in the boiler, as you can see here, the increasing the scale of what we lose here in efficiency is going to basically go to burning more fuel to get the same amount of energy out and the same comfort level. So this is part of the whole strategy of an efficient heating system, is to make, once you install that boiler, make sure it's maintained. You can see the flue gas passageways are blocked here. So this boiler here, in comparison to this boiler, would not fire as efficiently, you know, as it should. So service is a big part of the whole efficient heating system, and also comfort, right? You know, the more wear and tear of the boiler, the more time that boiler locks out on a fault because it can't, you know, the conditions in the combustion chamber aren't ideal. Of course, that's, you know, more service calls, more cost on that side versus keeping that boiler in a good state of operation. So all that stuff goes towards, you know, the efficient heating system. There's a high mass boiler, bigger flue gas passageway, so less service really maintenance required, but still it's got to be a strategy that we use as far as, you know, whether it's the homeowner, you know, making sure that we get our boiler serviced annually, or the contractor making sure we remind people. Viessmann's kind of thought of that in our controls. We have these addresses here available, and basically what we can do is we can actually put an alarm on the control on the boiler to let the homeowner know it's time to service the boiler. So if you think about those thermostats that are out there where you see the, you know, replace your air filter on your furnace, that's the same idea that this little alarm does on your control. We can set it up for address 21 for a run hours, so many hours of operation, and then the boiler is going to basically give an indication it needs to be serviced, or a time function in months. So you can basically use address 23 instead of 21 and say, well, you know, we're going to put 12 in here. So once 12 months expires, the control is actually going to flash the red light and a fault's going to come up on the screen. The boiler is not going to stop firing. It's going to continue doing everything in normal. It's just basically some sort of an alert that the control is trying to give, that, you know, when somebody walks by there, they look at that and see it's flashing. Oh, maybe I should give the service guy a call saying there's a fault on my boiler. So it just gives somebody some sort of alert. Once you go back in and now you do the service of the boiler, what you'll do as a contractor to reset this timer again is just go into address 24 and it'll be at a 1. you set it back to 0, push OK, and now it's going to time that 12 months again or run hours again until the next service is required. So that's in there as well to basically help give us a reminder that it's time to maintain that efficient heating system for the next year of operation. So that was a lot. There's a mouthful there that we dealt with today. I hope you guys appreciate you kind of hanging with me and staying in. I hope it was useful for you. If you, like I say, if we have any questions, so I can take those questions now. How you doing there, Mark?
You did such a good job. There wasn't any questions. I didn't have anything to do today.
Excellent. That's the way we like it, isn't it?
Well, it makes my life easy.
Well, again, like I say, I appreciate it. These are going to be archived, as Mark had mentioned earlier when we first started out. We're going to send you out the presentation here along, usually with a list of questions. If there was no questions, you won't get a list, obviously. But this was, I think, the last one for me for a little bit until the new year.
We might make you do one more.
Well, I'm always up for it. But I think the next time we are going to be meeting, Mark, you and I, is going to be when you do your presentation in November.
Yeah, VitaGate.
On Vito Gates, and that's going to be pretty. That's going to be a really
You're doing
interesting
commercial building automation interface. You want to belong to. You want to show up with the VitaGate.
Absolutely.
We're going to explain how simple it is and how easy it works, and take all the mystery out of it for you.
Yeah, we're just going to take that mystery wrapped in enigma and just pull out all the way, and so you'll be able to see what's going on there. So yeah, I look forward to that one. But yeah, if there's nothing else going on, and if you have any suggestions, so the people that are still with us, if if there's some topics or some things you struggle with on our controls or our boilers or something that you don't quite understand, you could always email one of us, Mark or myself, or post a question here, and maybe that's something that we present in the new year coming. Some topic that you guys have mentioned. So that's how we base a lot of our topics. Is we get some feedback from people, and we say, hey, let's make a presentation on that. It seems like people are having a lot of questions on it. Maybe it's something that's worth spending some time on. So we look forward to any type of information or suggestions you guys might have on future topics that we can present here.
Okay.
All right.
Scott, you did a good job.
Well, thank you, Mark, and thanks everybody.
See you guys on the next round.
All right. Happy Halloween. Take care.
Yeah. Right. Bye.